Hi everyone, my name is Chen-Yu Wei. Our work is adversarial online learning with changing action sets, efficient algorithms with approximate regret bounds. This is a joint work with Ehsan, Emamjomeh-Zadeh, Haipeng and David Kempe. Throughout the talk, I will use the example in these slides as a motivating example. The example is about horse racing. Consider a case where there is a set of horses. In each round, a subset of horses are chosen to compete with each other, and your job is to predict the winner of each round. If you predict correctly, you get a constant amount of money, let's say $20. This problem can be exactly cast as a sleeping expert problem, first introduced by Kleinberg et al. In 2008. In every round, the environment first reveals the available action set ST in that round, and the learner is only allowed to choose an action AT from the available action set. Then the learner suffers loss LT of AT. In the horse racing example, ST is the set of horses that are involved in the competition in that round, and AT is the prediction you made for that round. If the horse A wins, we set LT of A to be 0, otherwise we set it to be 1. Next, we see how to measure the performance of the learner. This performance measure is again given by Kleinberg et al. We define L hat as the cumulative loss of the learner, and L star as the cumulative loss of the best ranking sigma. Every time T, sigma would pick an action denoted as sigma of ST, which is the action that is ranked the highest in the ranking specified by sigma. To understand this sigma of ST, let's see an example. Let n equal to 5, and let sigma specifies the ranking 3, 4, 1, 2, 5 in order. If the available action set consists of 2, 4, and 5, then since action 4 ranks the highest among these 3 actions by this ranking, so this sigma function would return 4. The other example is similar. And recall that there are totally n factorial different rankings for n elements. And our benchmark L star is chosen using the best ranking. The regret is simply defined as the difference between L hat and L star. The goal is to make regret sublinear in capital T. If the regret is sublinear in T, then the average loss of the learner will be no worse than the average loss of the best ranking asymptotically. What are some known results for the competing with best ranking in the sleeping expert problems? The first is that it's possible to achieve a regret that is sublinear in T and polynomial in N. The way to achieve this is to use the hedge algorithm over all possible rankings. However, since there are totally n factorial different rankings, this algorithm requires computational complexity of n factorial per round, which is considered as a very inefficient algorithm. So a natural question is that whether there is any polynomial time algorithm that still has sublinear in T regret. Indeed, there are computationally efficient algorithms, but requiring the condition that either the loss vector LT or the available action set ST is IID drawn from some fixed distribution. Things become very different if both loss vector and the available actions are non-IID or adversarial. It has been shown that to get a sublinear regret in this setting, it is actually harder than PAC-learning DNF functions, for which polynomial time in N algorithm is not known yet. Because of this negative result, there has been not much result about learning in adversarial sleeping experts, and this indeed motivates our work. Our motivation is by the following question: is there a polynomial time algorithm whose performance is comparable to the best ranking when both the losses and available action sets are adversarial? To sidestep the hardness result, our idea is to relax the goal. We do this by consider the approximate regret. An approximate regret with parameter alpha, or alpha regret, is defined as the difference between the learner's total loss and alpha times the total loss of the best ranking. Alpha is some number larger than 1 called the approximation ratio. When alpha regret is sublinear in T, it implies that the average loss of the learner is no worse than alpha times the average loss of the best ranking. So with the approximation ratio defined like this, our goal becomes to find a polynomial time algorithm with a small approximation ratio and guarantees a sublinear approximate regret. This slide summarizes our results. Here we define some quantities because our bounds depend on them. First, K is an upper bound for the size of the available action set, and Z is the number of zero loss actions in each round. It's clear that Z is less or equal to K and K is less or equal to N. We've investigated two different feedback models. One is the full information setting, where you get to see all actions lost after each round. Another is the bandit setting, where you only observe the loss of the action that you choose at that round. Clearly, the bandit setting is much more challenging. Our first algorithm can deal with either full information or bandit setting, which is shown in the first row of the table. The approximation ratio is n, and the approximate regret is n squared. Although this algorithm works for a very general case, the approximation ratio is not satisfying. We are able to obtain better approximation ratio for some special cases when the losses are binary, meaning that the loss value is always 0 or 1, and under the assumption that there is always exactly one action that has 0 loss. We get an approximation ratio of order log k. This exactly corresponds to the horse racing example, where we only let the loss of the winning horse to be 0, and for all others, we set the loss to be 1. In this case, we can also deal with the bandit feedback setting. When the number of zero loss action is larger than 1, we have some preliminary results to get an approximation ratio of k squared when the number of zero loss action is 2 in every round. This is shown in the fourth row in the table. In the following slides, I will briefly go over the first two algorithms, and also I will assume that the losses are binary for simplicity in all cases. The first algorithm is called the level algorithm. It works for binary losses with any number of zeros. The algorithm is very simple, and it's actually a variant of an algorithm by Blum et al. Their algorithm is for some other applications, but the idea is very suitable for our problem too. In the algorithm, we record a quantity called level for each action A, and they are initialized as 0. In each round, the learner simply picks the available action that has the smallest value of level. If the loss of the chosen action is 1, then we increase the level of the chosen action by 1, otherwise we do nothing. With this simple algorithm, we can show that the approximation ratio is n, and the approximate regret is n squared. The proof is quite short and is actually an extension of the proof of Blum et al. The next algorithm is called HAT, that means hedges aggregated with tournament trees. This algorithm works for the setting where the learner has full information feedback, and importantly, in every round, there is exactly one action that has lost 0, while all other actions have a loss of 1. The idea of this algorithm is to reduce the sleeping expert problem to pairwise comparison. The HAT algorithm is built on the Bayes algorithm, which is simply the standard hedge algorithm or exponential weight algorithm with 2 actions. The pseudocode of the Bayes algorithm is shown in the block. Then these slides describe our algorithm. Basically, for every pair of actions, we initiate a hedge. So there are totally n choose 2 hedge instances. Then how will the learner choose the action AT? Basically, we will construct a tournament tree and set the champion of the tournament to be 80. Below, we give an example, assuming that the available action set consists of 1, 3, 4, 7, 9, 10. We place the individual actions at the bottom level. Then we pair the actions. Here we pair 1 with 3, 4 with 7, and 9 with 10. For each pair, we call the corresponding hedge instance. For example, we call the hedge that involves action 1 and 3 here. And recall that the hedge algorithm will maintain a distribution between the two actions. And we simply sample from that distribution and let the one is sampled go to the next level. Similarly, we can do it for all pairs. Then the second level, we do similar things, but now action like there's an action that cannot be paired, so we directly get it to the next level, and so on. Then we get the final output, and this will be the chosen action in that round. And after choosing this action, we will observe the loss, and then we will update a subset of the hedges. And so this head algorithm has the following guarantee. Under the specified condition, it has approximation ratio of log k and approximate regret of n squared. Finally, let's summarize our results. Our work gives first line of efficient algorithms to tackle adversarial sleeping, expert, and bandit problems. And we give some algorithm that achieve sublinear approximate regret bounds. For some further directions, we wonder whether there is an efficient algorithm with polynomial k approximation ratio, where the number of 0 is larger or equal to 3. In this paper, we deal with the case when z is equal to 1 or 2. Second, we would like to further improve the approximation ratio in all cases and provide approximation ratio lower bounds under computational constraint. And this concludes my talk. Thank you for your attention.